It's the holiday season.
Mm-hmm.
And I know for a lot of our listeners, that means that either we have a little bit more time, if you're in school or whatever, you have more time off, or your kids might be home with a little bit more time and you might want to do a fun holiday themed activity.
Okay.
And no matter what you celebrate, you've probably seen some of these festive plants.
Mm-hmm.
And so,
if you're an audio listener,
oh yes,
Melissa's currently gesturing toward this reddish, greenish thing between us.
it's a poinsettia, but it's supposed to be poinsettia according to the spelling and the Hallmark movie that I saw once about two people falling in love on a poinsettia farm. Anyway, but I probably call it poinsettia because that's how I've always learned it.
Right. Well, we don't really see the I in poin. It's not like poinsettia.
Right.
So.
Well, that one Hallmark movie I saw one time indicated, but you know what? Oh, well. Anyway, so.
I'm impressed that they were able to say poinsettia every single time throughout the movie. Like how many times did they say that word in the whole movie? Probably like 100 at least.
Probably it was a lot. I didn't see the rest of it because I was training. I was in a little hotel with my friend. We were going to go do a race the next day. So that's all I remember. Okay. So, if you've seen these plants, these poinsettia plants, I have a little bit of fun chemistry behind them for you today and an experiment that you can do based on this plant with this plant at home for yourself or with your kids. And if you're watching on YouTube, I'm even going to demo some of it.
Nice.
So it's a little bit different episode for the holiday season. I know this is coming out like the day after Christmas, but I know that people, this is not just a Christmas plant. This is a winter plant. So people will have access to them and it's pretty fun.
Nice.
All right. So you ready to get started?
Let's do it.
Hey, I'm Melissa.
I'm Jam.
And I'm a chemist.
And I'm not.
And welcome to Chemistry for Your Life.
The podcast helps you understand the chemistry of your everyday life.
Okay, so first I'm going to start with some fun chemistry facts.
Okay.
And a little bit of a chemistry lesson, but it's really a review of things that we've done before.
Okay.
And then I'll explain the experiment. Okay, so first I do want to shout out listener Vianette, friend of the show, loves the show. She was the first one who told me that these plants actually were originally cultivated by the Aztecs in what's now Mexico.
Wow.
Which I didn't know that.
Cool.
And they're known by their native name, Quetzalcoatl.
Whoa.
Hopefully I said that right. It means withering flower. And it's not just a Christmas plant. It is also used in religious ceremonies by the Aztecs. And it was used in traditional medicine. And we call it poinsettia because the first U.S. ambassador to Mexico sent it back to his family in the States, and they cultivated it, and his name was Poinsett.
Ah.
So there we go.
Wait, so you said it was used in medicinal ways? Do we know what or how?
I don't know what, but this is a little bit of a sneak peek, but the leaves do secrete latex, which we've talked about before.
We have talked about that, yes.
And that is to protect the plant, but I also wonder if that has some medicinal properties as well. And it like really secreted the latex. I like cut up the leaves and it was beating out. It was crazy. Wow. I took a video. It was really cool. So, and the video is probably already posted, although Jam hasn't seen it yet. So if y'all want to go check out our socials, you can see it.
Excuse me, but don't look fast because I haven't seen it yet. So wait, let me catch up, please.
I like to surprise Jam with what we're going to talk about. And so I made a whole little video and didn't tell him anything about it.
Yeah, and I don't, I prefer that too. This is one of the few areas where I don't, where actually I'm okay with being surprised.
Yeah.
Because it is actually nice to not have to pretend like I'm learning something. It's like, good to fully be learning it and have no heads up about it. But for the most part, I don't like surprises. This is the one exception. You are welcome.
Okay, so the chemistry behind this plant. Okay, the bright red leaves are these colors. I want to call them flowers, but this is another fun fact. These are not flowers. The red part is not a flower. It's a modified leaf. It's called, I wrote it down, but I'm not there at my notes yet. So these red leaves get their color from a highly colored group of compounds called anthocyanins.
Oh, we have used that word before.
I was going to ask if you remember where else we've heard of that word. When else have we talked about anthocyanins? It's okay if you don't remember.
So say what it is again. Like what is anthocyanin?
It's a red pigment.
It's a red pigment.
Highly colored.
Is that we're talking about leaves changing color in the fall?
Yes.
Okay, because it's like they were breaking down at different times, which revealed the redness of the leaves.
Yes.
Okay.
And that's what I suspect happens here. So when the winter months come around, a hormone is released in the plant that makes some of the leaves turn red. You can sort of see like some of them are on the plant we have here. Some of them are still kind of green. My guess is this hormone is released when, they get exposed to a certain amount of darkness. And what it actually does is probably kill off the chlorophyll. And there is probably already this anthocyanin is in the leaf no matter what.
Right.
And then my guess, this part I'm guessing on, but I'm guessing that's how the leaves get modified is they just leave that red behind, but it kills off the chlorophyll.
I see. So you don't think is that these top leaves kind of got embarrassed in some way about something?
Well, and some of them look like new growth. So I wonder if they just maybe the plant produces leaves without the chlorophyll at all or something. I'm not 100% sure. But what I am, bract is the name. I just remembered the bracts. BRACT. So I'm guessing that there's something in the plant that makes these leaves have only the red stuff, but I bet the red stuff was already in it.
Okay.
And then the anthocyanins and the chlorophyll is just what's missing, and that's why they appear so red.
Got it. Interesting.
So yes, we used anthocyanins there before. They are the same colored pigments that make trees red, or the same class of colored pigments. And they do something else really cool, and you've actually also seen this before.
Okay.
They can be used as a pH indicator. Do you remember when you did something with that?
I do. What was it that purple cabbage stuff? Was that what it was?
Yes. The red cabbage.
Red cabbage.
Yes, if you take red cabbage and you blend it up.
Yes.
That's what you did, right?
Yep. Wow, that was a long time ago.
That was a long time ago. So that's why I figured it'd be kind of fun to revisit.
Nice.
They also use anthocyanins.
Okay.
So the chemistry is the same. So I'm not going to go in detail on it again. Okay. It's sort of like a fun revisiting the chemistry episode. But so I'll say that when molecules are visible to us, is you have to have light, and then they will be they absorb light in the color or in the visible region. And whatever color they absorb, it's like the opposite color is what we see. So these red ones actually absorb a lot of color in like the blue area of the spectrum.
Okay.
But the way that works is if you have a molecule with a lot of alternating double bonds, those tend to they have like a gap. It's called the HOMO-LUMO gap. So the HOMO is the highest occupied molecular orbital, or that means that there's an orbital, like a space where electrons like to hang out, that's lower energy, but it has electrons in it. And then the space between the lowest one that has some electrons in it, or the highest one that has some electrons in it, and the lowest one with no electrons in it.
Okay.
There's a space there, and that space is the amount of energy that can be absorbed to excite the electrons up to the next rung. So we've talked about that a few times before, but basically when electrons take in energy, they sort of jump up to the next energy level. Or they kind of move away a little bit more from the center where the center of the molecule. Okay. So they need energy to do that, but they can only absorb energy in these specific amounts, and that amount corresponds to this gap, the HOMO-LUMO gap.
Okay.
So it's like, can you absorb enough energy to get us right to the next rung of the ladder? And too high won't work, and too low won't work. It has to be the exact right wavelength of energy. And that gap, the like size of it or wavelength, can be adjusted based on features of the molecule. So if you have more alternating double bonds, it will change it. If you have less, it'll change it. If you can add sometimes like functional groups to make it change ever so slightly. And so that's sort of the anthocyanins take advantage of that, is there are a class of molecules that are highly colored and they have functional groups. And so when we expose them to acids and bases, the functional groups interact with the acids and bases. And those little changes in the electronic environment will cause the nature of the molecule to shift enough that it alters that gap of the amount of, or the wavelength of energy that can be accepted. And therefore, the color that we see is changed.
Okay.
And that is how you get a pH indicator.
Dude, that was so crazy that, like, I think whenever I did that experiment, you, as usual, didn't tell me anything about.
Nope, didn't tell you anything.
And I just didn't think that it would never have occurred to me if something like that did exist.
Yeah.
In cabbage.
Yeah.
Like, it was like, wait, why are these different shades of like purplish? And then once you explained it later, it kind of made a lot more sense. But it was like, I would never have thought that there could be something kind of perfectly baked into plants that would do that.
Yeah. It's very cool. And you can go watch that episode. It was a chemistry at home episode that we did. It's on YouTube, I think, of you trying it. And so I'll explain at the end of this episode what you can do something similar with these that I made a little video on, so you can go watch that as well. But I wanted first to have you tell me back that little chemistry lesson.
Okay.
And then I'll see if there are a few other facts I still haven't shared yet. And
then. This is going to be hard for me to do. So, the anthocyanin is a dang it. I can't do it, I don't think.
Okay, did I go too fast, do you think?
Yes, and I didn't know I was going to have to tell you back to you.
Oh, because it was so quick.
And because you're like, we're not going to go way into this, but we're going to review it for a second. Okay. So I was like, yep, I know this stuff.
I remember.
Yep, okay, I was there, and I was thinking, man, how crazy that experiment. And I was like, letting myself just kind of
Okay, well, let's do it in parts. So, if light is how is light absorbed?
Yeah, so there are there's the backwards thing that always freaks me out about how light absorbs. There's obviously the spectrum of wavelengths, and so what it absorbs, which wavelengths like kind of brackets it absorbs, is the opposite of what it reflects. Correct?
Right. So or what we perceive.
What we perceive.
Yeah.
And so there's the spectrum of different colors that. Invisible light, at least, where if something has is it highly conjugated?
Yes. Then a lot of alternating double bonds is what conjugation means.
Alternating double bonds. Then
and we have episodes on that. I think antioxidants is one where we've talked about this before, and I think maybe bleach. So we've talked about this before for sure.
So if that's the case, it's got the alternating double bonds, a lot of them highly conjugated, then it absorbs, it ends up reflecting a lot of the brighter colors like reds, right?
Just any visible light.
Any visible light, which means it absorbs... it doesn't absorb as much of any of those colors.
Yeah.
it may be absorbing other stuff, but not visible light.
It'll absorb somewhere in the visible region.
Somewhere in it. Okay.
So it takes in some, and then we perceive the stuff it doesn't take in.
Right.
So I Googled, and this could be like a good visual for you if you want to Google as well. Just like food color absorption spectrum. And it'll show you like, red food coloring, what we see as red, absorbs all the blue light.
Right.
And so then there's no blue light left, so we see it as red. So that's what's happening here probably too. But then blue food coloring absorbs all the red light. So there's no red left on the spectrum. So then all we can see left is blue.
Right. And it does something, whatever's opposite on the like color wheel or something like that?
Yeah. It's like it shows its complement primarily.
Got it.
Because that's like what's left up of the light, like what you have left in your light. If you take, the whole light spectrum and you absorb all the red, what you're going to have left is going to look blue kind of thing. So, and the way that we determine exactly what wavelength it absorbs at, because each of these wavelengths corresponds to these different colors, and then the opposite color that we perceive is based on that gap. Do you remember what that's called? It's kind of a weird name.
The gap is the... Dang, I think like as soon as you say it, I'm gonna get it, or I'm gonna remember it. But
homolumo.
Okay.
Homo stands for highest occupied molecular orbital. So, like if we have a ladder rung of orbitals, the highest one is the highest one that still has electrons in it.
Okay.
So like I always picture it as a ladder. That's not really like, technically it's these areas where electrons like to hang out. But if it's easy to visualize it as a ladder. So imagine you had a ladder that was like, had somebody, let's do Santa's elf standing on each of these little things.
Right.
The highest rung where there's a little elf hanging out is the highest occupied rung. And then for that elf to climb up to the next row, there's a specific gap, a space that they have to be able to reach. And so that's the highest occupied rung. And then the lowest unoccupied rung is going to be the next one that they're going to try to get to.
Right.
And that gap if it's electrons instead of Santa's elves, that gap determines what wavelength is absorbed. That's how much energy that electron can absorb to hop up.
Got it.
And so if that electron absorbs that energy, it's increase in, it's like the electron gets excited, and that is the exact wavelength that needs to be absorbed for us to see these certain colors. So if you can change the electronic environment, you can like make that gap smaller or bigger.
Right.
And we've talked about that a lot before on other episodes about light. And even I think we talked about it maybe... Did we talk about it on the Green Fire episode? It's come up a lot.
Yes.
So by having acids or bases in the presence of these already highly colored molecules that happen to have functional groups that tend to react, and functional groups we've talked about before are like groups of atoms that act in certain ways. So these anthocyanins have the like 1-2 punch of lots of alternating double bonds. Their homo-lumo gap is perfectly situated in the colorful area. And then we've got functional groups that are easily tweakable. They want to interact with acids and bases. And when they do, it changes the electronic environment. And when it changes the electronic environment, the electrons act differently. And it alters how much space they need to move to absorb light. And so that then alters the color that we perceive.
Got it. Okay.
Make sense?
Yes, it does. Definitely.
Okay, great.
Yeah. And I feel like what's funny about this too is that like this whole area is so fascinating. The fact that it combines the light stuff always makes things so hard for me to wrap my head around and remember.
Me too. Yeah.
But also, it's the kinds of questions we get tons of, like, even though we did the why do leaves change color in the fall episode quite a ways back, we get asked about that all the time. People who don't know that we did that, and we've even rebroadcast it at least once.
Yeah, comes up a lot.
But it is kind of crazy. Like the answer is more complicated than probably I would have expected, but also like very fascinating.
Yeah.
And it's just kind of strange that it happens to work out so perfectly like that.
Yeah.
Because it's like, is that really necessary? Would be my question.
What do you mean? Is that necessary?
Like the fact that it is so well situated in that range that human eyes are seeing.
Yeah.
You know what I mean? And like, we obviously know other creatures have slightly different, whatever, dogs and stuff.
Yeah. And I think about that a lot too, is like other things that appear colorless to us don't absorb in the visible region. Mm-hmm. And so it's like we perceive all of the light, and that's why they look white, Right. It's just, it is very weird to think about.
Yeah.
And it's something that I struggle to even wrap my mind around. So it probably translates to it being hard for you. If it's hard for me, then I don't always do the best job explaining it.
No. Yeah. I mean, I feel like it's always hard. And there's a few times, like, I think one of those I remember struggling with a lot back a while ago because of this, but it still was very interesting to me. It's just like, oh, my brain wants to get it. When we did the one about mirages.
Oh, yeah.
Because that had to deal with a lot of that, plus just the fact that they're so weird. And
yeah, I kind of forgot about that.
That one, I have a distinct memory of like struggling to like really hold on to and like retain a lot of what we're talking about. But it seems like the light stuff is one of the most common areas of that for me.
Yeah.
Where I'm like, I think I tend to remember the most basicest stuff. Mm-hmm. Energy level ladder thing. We've talked about that so many times. Every time we talk about it, I'm like, oh, right. This is not intuitive to me. I'm having to like kind of get back out of my, like the way I have always thought about it.
Yeah.
That is not scientific.
Yeah.
And get into a whole different headspace that's not connected to how I operate most of the time. But the ladder thing helps a lot.
Kind of surprise you.
I like the rungs ladder thing, even though I know it's not actually rungs, like you said, or whatever. And once that visual always helps me kind of get back into like, okay, right, go over to ladder rungs, energy levels,
brain
coming back down, that kind of stuff.
And it did surprise you didn't expect it, so that was kind of on me.
It's okay. This is what we do. So
I think it was the way I framed it. But I do think if you're doing this with your kids and you're like, oh, this is a fun science experiment, or with, your nieces and nephews, whoever, if you want to be the cool auntie and bring the fun science experiment over the day after Christmas, sorry. I will say you can talk to them about this on like a much lower level. So just asking them like, oh, what color do you think it's going to be? Get them to make a guess, and then add household things that it would, they would see on a regular basis. Try to get them to guess why it would change colors, things like that. So here is what you can do as your little science experiment. You can take the leaves of this type of plant, these poinsettias. You can cut a whole little flower bunch off. There is flowers in the middle, and then the red leaves surrounding it, and cut those leaves up into a little thing of water and then boil it. So my husband was like, you're basically just making tea. And I was like, yeah, 100%. But the fresh leaves. So you make your poinsettia tea. It's smart to wear gloves because they do, like I said, when you cut it open, they will emit latex. The plant will. And it really was a lot. There was like latex on my fingers. It was crazy how much it was dripping.
That's surprising. Wow.
It was surprising. I was like, whoa, what's happening? And so you can wear gloves or something, because I think it can sometimes irritate people's skin. Boil it for, I think I just did like 10 minutes, and then I turned the heat off and let it sort of sit in the hot water until it cooled down. And then I filtered it through a coffee filter. And then I dried the coffee filter. So I filtered it through. I kept the liquid, and I let the coffee filter dry. And you can do two different approaches. You can either use the liquid, which is like a liquid indicator, and you can add liquids from your household to it. So like you can add baking soda mixed with water. You can add, if you have like an alkaline water, or if you have lemon juice or what I brought was to show on the YouTube video was vinegar and baking soda mixed in water. And so you can either add those directly to the liquid that you have, or what I did when I dried my little coffee filter is I made basically pH paper that we can dip into things. So I have it off to the side so that Jam couldn't see and guess, but I'm going to bring it and show the people on YouTube, and we'll try to describe what's happening for the people listening on audio.
Okay. I noticed that bin over there. I didn't even think about it.
Hopefully I don't knock this over onto our recording equipment.
Yeah, I hope not. Okay, I'm guessing the red ones is poinsettia water, and the clear ones is not.
Very astute observation.
Did I get that right?
You got that right. Okay, so here is my homemade pH paper. So this is the coffee filter that I filtered the poinsettia leaves through.
Okay.
I composted the leaves. So, and this is like, don't eat poinsettias. They're not toxic, although they're often thought to be toxic. They're not toxic unless you have like a ton of them. It would be difficult to have enough to actually hurt you significantly, but they're still not good for you. But I've heard they also taste terrible. So, Jam, I will have you open one of these jars, and I don't remember, one of them is vinegar and the other is baking soda. You'll probably be able to tell from smelling,
right?
But you could also just very lightly dip this in here, and if it turns pink, it is acid, and if it turns like bluish gray, it's base.
That would appear bluish gray to me, right?
Yeah.
So this means this is the baking soda?
That is the baking soda.
Okay.
And you can just set it in the lid if you want and let it dry in there. It doesn't matter,
So this one should be the acid, vinegar, acetic acid, if I remember correctly.
Yep.
Nice.
It looks at first like it's just getting wet, but it gets pinker and pinker.
Yeah, that's crazy because if you hadn't seen this one, it would just seem like, oh, it's just getting wet and things look darker on their wet sometimes. But it's like, no, this one was the same color. And turned a totally different color.
Yes, absolutely. And a fun thing to do is get a little bit in a bunch of small jars or small containers, like you could do plastic cups or something, and like sort of try all these different household things and see how their color might change.
Is this little part right here that's darker where I touched a second ago?
Maybe, I'm not sure.
Because it's like...
It did get a lot darker, and my other one didn't do that, so I'm not sure why.
That's crazy.
Okay, so, and that's one way to do it, is you can make your own pH paper, and you could go around just like testing all kinds of things in the house, and these... I think they're a little bit like less mess, and a little more controlled. Right. So that's kind of nice, is you can test all kinds of things in your house and be like, this is acidic, this is basic. And that could be really fun for kids. You can also look up things that have a known acidity or basicity and like make your own pH scale. And then, if you have older kids, like try to guess, where do you think this is going to show up on the pH scale? Where's carbonated water? Where's regular water? So that could be fun. Okay, so that's one option, is you make your own pH strips. The other option is to use the water and pour things into it and see if the colors change. So that's what we're going to do next. Okay. So we have 3 glass jars. These are spice jars that my husband bought because he made his own habanero powder because he's crazy.
Yeah, forgot about that. That stuff couldn't be heard.
Okay, so I'm going to open each one of these, and I'm going to let Jam pour a little bit of acid into one, a little bit of base into the other, and then we'll leave the third one as a control.
Nice. Okay. This one's the acid going into this first jar here. Not too bad. Wow. Should I add more? Or do you think it's okay?
No, I think that's good. So that one's, it's like a brighter pink compared to the original.
Uh-huh.
And technically the original is showing you the pH of something that's neutral.
Oh, yeah.
And now I'll add a little bit of base.
Wow, that one's super different.
Got a lot darker, I would say, than the other ones.
We might need to hold those up. I think the...
I wish we had a white.
Here.
Oh, that's a good idea. So there you can kind of see, but
nice and visible, yeah.
The more acidic things you'll get, it gets like a brighter pink, and so you can kind of get it on a nice scale and get a variety of colors. And we've linked some different references where you can go and look and see how they used them. But yeah, there's a little bit of chemistry at home that you can do over the holiday break if you have access to some flowers and some bored kids, or if you're bored yourself and you just want to see. I had fun with it. I enjoyed making it.
Yeah, it's awesome. Yeah, I feel like there is like you said already, like a version of this for all sorts of age groups, because you really could make it more interactive, more complicated, more things you could pour in and test. You know, kids the age of like my 4-year-old, for instance, so just doing like these 3, like the way it already was, and then acidic, and then more basic, and just having the comparison of 3 different ones by plenty, and would be fascinating enough for him, and he's only 4, you know?
Yeah, and he could just pour all kinds of things into all kinds of things, and it would be really fun, and you could make sure it was safe by only having these certain ones, you know?
In order to get the initial poinsettia leaf water before you add anything else to it, how much leaf did you use and how much water did you just to kind of get a good...
I cut one whole chunk of red thing, and you can see in the video, I can show you the video after, but I used one whole red thing, and then if I had to guess, I would say it was probably like maybe 200 milliliters of water.
Okay.
But it, what is that? Like I don't remember the conversion.
It's like 29, I think, milliliters per ounce.
29 milliliters per ounce. So that's like, quick math. 200 divided by 30. 6 ounces. I did more than that.
Okay.
All right, 6 times 30 is 200. Whew.
6 times 2 would be 180.
7 times 30.
Okay.
I think it was more than 7 ounces. Okay. But it's hard to say. But you could probably do more and just let it boil a little bit longer.
Okay.
And I would say, you know, treat it like a science experiment. So don't let them touch the water unless they have gloves on, you know. But also, it was pretty fun even to just like cut up the poinsettias and put them in the water and then boil it. And so, yeah, I think it could be really fun. And I was going to say, for the age group of like your son, just showing the color changing when you have different things in and explaining like, when we mix 2 things together, there's a chemical reaction. Like sort of the basics of chemical reaction. What does that mean? And then like colors change. We're doing a chemistry reaction, you know?
Yeah.
It might just seem sort of like magic to them at this stage, but it's still like, okay.
Yeah.
You're giving them the language, you're letting them try things, or getting the experience of experimenting, and they get to try like, what if I add this? What if I add that? You know? Like, what if I add lime? What if I add, you know, whatever?
Oh, yeah.
And things that they're used to seeing, would it change the color?
Totally. There's so many like just household liquids that you really could grab quite easily that would have a different effect. I didn't think about like, we always have like lemon juice or lime juice in the fridge, and, you know, like everybody's got vinegar or baking soda handy pretty much. And yeah, that's awesome.
And they can just talk about like, what color do you think this one will change? And let's line them all up. And then as they get, you know, bigger kids, you can have more in-depth conversations, but it would still be fun.
Can I ask you this? What are some things, because I can't think of any off the top of my head, but I'm sure as soon as you see stuff, I'll be like, oh yeah, that are basic that would be in the average household aside from baking soda?
That's a good question. So bleach, but the thing with bleach is bleach will initially react with the anthocyanins, but then it'll keep reacting and it'll destroy some of those double bonds, and that might remove the color, which is how bleach works.
Interesting.
I think fish a lot of times is basic. Ammonia, so if you have like window cleaner, that could be basic. That's harder to think. I actually think, alkaline water, people have been doing alkaline water.
Oh, yeah.
And that would probably be somewhat basic.
People are doing it.
Yeah, people are using it.
Yeah. Uh-oh.
I meant more companies are doing it and more people are having it in their homes.
I was thinking
I maybe like detergents might be ever so slightly basic, I think. Let's see. I Googled very quickly.
I was going to say that because like Arm & Hammer makes like toothpaste and stuff. And I'm guessing that also has baking soda in it. Some of those lids, or things like it, which would be basic. But
I looked up what are alkaline things in the average household because basic things are like,
right,
furniture.
Right.
AI, who knows if this is accurate? They said baking soda. Oh, yes. Drain cleaner is sodium hydroxide. That would be dangerous for a littler kid, but could be fun for an older kid.
Yeah.
Some types of toothpaste. Oh, yeah. And antacids like Tums.
Oh, nice. Cool.
Again, not something that a kid would be interacting with a lot, but that would definitely be one.
Yeah.
Bleach and ammonia. Yeah, we already mentioned those. So, those are some ones. I don't know. Some people said maybe some food, and that could be fun. It's like what other foods would be, could come up. This says the alkaline diet: fruits, nuts, legumes, and vegetables.
Cool.
I don't know. That's a quick Google search. So who's to say? You could try it. And that would be a fun experiment.
Yeah.
They could put their, blueberry juice in there or whatever.
Oh, yeah.
Squeeze their broccoli in there.
Nice.
So yeah, your coffee creamer. See if that changes it.
Oh yes, yeah, that'd be interesting. Pick something that already has a color.
Yeah.
And
you can let them do that kind of thing. Like, what do you want to put in here? Is there anything exciting to you? So, all right. Well, this is kind of a little bit of a different episode, but I hope that this is a fun one for you. I thought it was really fun. Let us know if you like this, if you want us to do more like this. And we can bring back some of the chemistry at home experiment series.
Nice.
So yeah.
Thanks for teaching us. Thanks for taking us to a bit of a different cool activity we can do over the holidays or anytime. These were very fun to do back when we were doing those. And yeah, I didn't realize. I guess I could have thought about it, but because it's been so long since we did that, I don't think I really thought about the many things we could do that with that isn't just the cabbage. So the fact that poinsettias and other things like that are a good option.
And I think people have a lot of them around this time of year. Yeah. So if you need something to do,
nice.
Yeah.
Well, thanks for teaching us. And if you'd like to learn more, or if you have a question yourself, something you think may be chemistry in your everyday life, or even a follow-up question to this one and experiments and stuff like that, other episodes you've already listened to, you can reach out to us on our website at chemforyourlife.com. That's chemforyourlife.com to share your thoughts, ideas, questions with us. If you'd like to help us keep our show going and contribute to cover the costs of making it, you can join our super cool Chem community of patrons on patreon.com/chemforyourlife. That's patreon.com/chemforyourlife. To join that super cool community, you get perks, ways of us saying thank you to you, to keeping the show going, keeping it free for everybody else. We thank you by sending you thank you notes, by posting behind-the-scenes content, giving you an ad-free version of the show, just stuff like that we really appreciate you, and thanks for keeping our show going and keeping it free for everybody else. But if you're not able to do that, you can still help us by subscribing on your favorite podcast app, rating, review on Apple Podcasts. Those things help us share chemistry with even more people. Subscribing on YouTube channel, giving a comment over there. Those things help us be discovered, help other people to have chemistry in their everyday life.
Absolutely. This episode of Chemistry for Your Life was created by Melissa Collini and Jam Robinson. Jam Robinson is our producer, and the episode was made possible by our financial supporters in our community. And like Jam said, it means so much to us that you want to help make chemistry accessible to even more people, and we want to shout you out. So We want to thank Chris and Claire S., Hunter R., Katrina H., Lynn S., Scott B., Stephen B., Tim P., Brian K., Chelsea M., Dorian V., Elizabeth P., Heather R., John T., Jesse R., Latila, Rachel R., Autoclave, Avishai B., Chelsea B., Sierra L., Cullen R., Emerson W., Erica B., Jacob T., Jeanette N., Julie S., Christina G., Sarah M., Suzanne P., and Venus R. What an amazing list. It's so exciting that we have so many people as a part of our community. So thank you so much for all that you do to make chemistry for your life happen.
And if you'd like to learn more about today's chemistry lesson, today's chemistry experiment, you can check out these references for this episode in our show notes or in the description of the video.
Yay, chemistry!
Yay, chemistry! All right, now I get to drink these, right?
Don't do it.